revise again. Okay, Chapter 8 is all about rational functions. And we use rational functions and all sorts of calculations. One of those is surface tension of a a pond surface. Like, how can some spiders please stop talking? I've started the lesson. Sign the behavior log on the way out. Okay. Thank you. Rational functions help explain how surface tension allows some animals to tread across a pond's or ocean surface. You've seen those lizards that can just walk on water. Well, that's because of surface tension. And if you can accommodate the surface tension of water, we could walk on water. So how can you graph rational functions and solve rational equations? That's what we're going to be learning about in this chapter. So how to graph rational functions and solve rational equations. So 8-1 about the inverse variations was to recognize and use inverse variation and to use joint and other variations. We're skipping this because by the time we're through this lesson, which is quite, I think you'll find quite easy, you will have had 8-1 as well. One of the things I do want you to know from that is the essential understanding. If a product is constant, where a constant is positive, a decrease in the value of one factor must accompany an increase in the value of the other factor. So it's when in an inverse, if any product is constant and is positive, if you decrease the value in one factor, it's going to accompany an increase in the value of the other. So they're related. And we talked about this in Algebra 1 to introduce slope. We talked about direct variation, remember that? So that comes into play. So like direct variation had the form of y equals k times x, where k cannot equal 0. Because in y equals k times x, if you make k equal to 0 here, you're going to end up with y equals 0. So it just sort of blows the whole equation. So k cannot equal 0 in a direct variation. It's got to have some constant of variation, k value, other than 0. Now, an inverse variation can have the form of x times y equal k, y equals k over x, or x equal k over y, where k cannot equal 0. Okay? When two quantities vary inversely, as one quantity increases, the other decreases proportionally. So they're related by that k value, that constant of variation. For both inverse and direct variation, k is our constant of variation. And that is what we worked on in Algebra 1 and what we worked on first semester was direct variation, y equals kx. But in all of these, the k is your constant of variation. How many of you are in geometry currently? Wow, everybody. So, good. All right, so it says you've seen many variation formulas in geometry. So you've seen many of these formulas. Some, like the formula for the perimeter of a square, are simple, direct variations. Others, like the volume of a cone, relate 3 or more variables. 3 dimensions, 3 variables, right? Length, width, depth. When one quantity varies with respect to 2 or more quantities, you have a combined variation. When one quantity varies directly with 2 or more quantities, you have a joint variation. So 2 or more combined directly with 2 or more is joint variation. The volume of a cone varies jointly with the area of a base and the height of the cone. Like volume equals k times base times height. So here's some equations of the combined variations, where z varies jointly with x and y. So z equals kxy. So it's jointly with x and y. And then the next one, use different color. Z varies jointly with x and y and inversely with w. So z with x and y, and then inversely with w. In the third one, z varies directly with x and inversely with the product wy. So here's my, let me get a different color. So with z varies directly with x, see it's in the numerator, and then the inverse things are always in the denominator. So inversely with product wy. So do you see if it's just numerator or just a whole number? That's just a joint variation. When you add the fraction to it, the denominator parts are your inverse parts. Okay? Now, moving on into 8.2, let's look at this first problem here. It's just this opener, lesson opener, to get you thinking about things that are related with this lesson. So 8.2 is about the reciprocal function family. Reciprocal. That's stuff that was probably introduced in 6th, 7th grade, and we've worked with it ever since. So our objective is to graph the reciprocal function and to graph translations of reciprocal functions. So we're going to learn how to graph it and translate it. Sounds familiar, huh? Don't you think it might involve these three things? A, H, and K in some kind of equation, where A is our stretch or compression, H is our horizontal movement, and K is our vertical movement. So let's look at the lesson opener. For a class party, the students will share the cost for the hall rental. Each student will also have to pay $8 for food. The cost of the hall rental is already graphed. So here's the graph of the cost per student of the hall rental. What effect would the food cost have on the graph? And explain your reasoning. So I've blown this up. There it is. So this is just the graph of the hall rental. And they want to know what effect would that cost, the $8 per student of the food. What would that do to this graph? So look, our title says it's about the cost of a class party. Okay, now on the axis, on the y-axis, this is your cost per student in dollars. And your x-axis, you've got the number of students. Okay, so right now, this is just the graph of what it cost the students to rent the hall. Right. So for 80 students, the cost per student becomes $3. If I only have 40 students, the cost for each student becomes $6. Okay. So the more students, the cheaper, right? So you want to get as many students to come to these things as possible because it'll cost less for everybody. Now, what happens when we add the $8 cost for each student to have food? What's going to happen to this graph? And that's what I want you to think about and write about in your journal, and we'll revisit this in about a minute. This thing's been wonky all day. Okay, now I would like for you to turn to your aisle buddy, or if you don't have an aisle buddy directly across, pick one close by, and discuss your reasoning. What's going to happen, and discuss why. Okay, I heard a lot of the word stretch over and over and over. And hold that thought. Let's look at what's happening here. It says if I have 40 students, my cost per student is $6. But what happens if you have to raise the price for each student? And it's constant, no matter what. It's going to be a flat $8 per student to eat. So if we add the food to this, don't you think it's going to rise the cost for each student by $8? So when we have one student, well, they don't even have the cost there, but don't you think it's going to raise the cost per student by $8? So if we were at $6 per student for 40 students, now we've got to tack on $8 to that, right? Because it's going to cost each student $8 extra to eat. So it would be a 6 plus 8 here, which would be 14. So it's shifting this up by 8 units. And it would do the same thing here. It's going to add 4 plus 8, which is 12. So it's shifting this up 8 units. Everything, it shouldn't be a stretch. It should just be a translation of just moving it vertically up by 8 units. Okay? Does everybody see that? Does anybody have any questions on that? I love to hear the discussion. I love to hear this class taught because you guys are always involved and you do good work. And I always say, when you're discussing and you're trying, there's no wrong answers. So just, go for it. And let's see where we go with it. And if we come up with something incorrect, then what are we going to do with it? We're going to learn from it. All right? So, is everybody good with this? So, you still see that we're going to have these H and K values in our A. A would be the stretch or shrink. The K is which translation? Vertical or horizontal? Vertical. And the H is horizontal. So what kind of translation happened here? Was it the H value or the K value? The K, because it shifted up by 8 units. All right, very good. All right, so let's look at some more words. So reciprocal function. Functions that model inverse variation have the form f of x equals a over x. F of x equals a over x. And x can never equal what? 0, because that would be undefined. When we talk about fractions, we're saying how many total pieces of something do I have? Let's say 8 pieces of pizza, and I ate 2 of them. So I ate 2/8 of that pizza. There was 8 pieces total, I ate 2. You can't have 0 pieces of something. Well, that didn't work, did it? So I can't say I took 2 pieces from nothing. And in fact, if it's nothing, why are we even trying to represent nothing? You can't represent nothing. So that's why we say 0 is undefined. You cannot have 0 in a fraction. It's something that doesn't exist, all right? So that becomes pretty important here. What if I had this? What can x not equal? Overall, the denominator can't be 0. But what would make this 0? Say it again. -6. So here we're going to say that x cannot equal -6, because then you would have -6 plus 6 equals 0. And then we're back to the undefined fraction. I ate 5 pieces of nothing. Well, where have you been? Not on this planet, because that doesn't exist here on Earth. All right, so f of x equals a over x. X cannot equal 0. They belong to a family whose parent is the reciprocal function. F of x equals 1 over x, where x cannot equal 0. So they're saying this f of x equal a over x. So we can say that a might be equal to 5. Okay, so this is going to be a translation of our parent function here, 1 over x, right? So this is about having something in the numerator, which we're going to call our a value, but it comes from this parent function, f of x equals 1 over x. So we need to learn, what does this f of x look like? It's going to do something like this, and I'll show you a few little rules to help you graph it quickly. And then this a value is going to either stretch it or shrink it. And then we're going to learn about the h and the k in just a minute that would shift them around. Okay, and we'll also talk about what does this negative sign do. Okay, but the parent function of all these is f of x equals 1 over x. So just like all of our other chapters and sections where we learned about a parent function and how to apply the translations, same thing here. This f of x equals 1 over x, that's our parent function. Okay. So the essential understanding transformations of the parent reciprocal function include a stretch or compression, or a shrink. They sometimes call compressions shrinks. You could say stretch or shrink. A reflection, that's when the a value is negative, right? Horizontal and vertical. So there's my a, my negative sign, my h, and my k. So we're going to apply all that to f of x equals 1 over x, or a over x, where 1 over x is the parent function. Okay? Any questions so far? All right. So here's the parent function graphed. And we're going to talk about the equation that includes them all. So the general form of a member of the reciprocal function family is y equals, here it is, a over x minus h plus k, where x cannot equal h, because if x was equal to h, then you would have h minus h, or a 0 down there. So we have to make sure that we avoid those zeros, okay, in the denominator. So there's the big picture of all of them together. Y equals a over x minus h plus k. And the whole parent function of this is y equals 1 over x. Okay? Now, when we graph this, I'm going to point out a couple of things. Each one of these marks are 1. So notice that in the parent function, you're going to meet at 1, 1, and negative 1, negative 1. And then I always say at about 4, it's really, really close to the axes, x and y. And that's what I always use to graph quickly the parent functions of y equals 1 over x. And then the negative 4 and the negative 4. Okay, these are in the first and third quadrants for the parent function. Okay, then you would just connect it with a smooth line. And that's how you quickly graph the parent function. So 1, 1, negative 1, 1, around 4s and negative 4s. It gets really close to the axes. It's never going to touch the x-axis or the y-axis, and it's never going to cross them. Okay, those are both asymptotes. Okay, x is the horizontal asymptote, and y is your vertical asymptote. All right, so I'm a little ahead of myself. So let's look at what happens to these things as we start shifting values in this formula. So as you know, the inverse variation formula, y equals a over x, that a value is going to do the shrink or the stretch. And if we make it a negative, it's going to flip it. Okay, so it's going to flip it over the x-axis. So this comes down here, that goes up there. Okay, so if you've got the negative, it just shows up in the second and the fourth quadrant. Okay, and the h and k is going to shift those vertically and horizontally. So let's look at that. On problem 1, and I hope you have your 8-2 out of your workbook. If you don't, make sure you grab it. So it says, what's the graph of y equals 8 over x, where x is not equal to 0? Identify the x and y intercepts and the asymptotes of the graph. Also state the domain and the range of the function. Well, I'm going to tell you this now. Domain and range for all these, x can never equal 0. So y is never going to equal 0. So it's never, your domain and range is always going to be all values except x can't equal 0, all values, but y can't equal 0. Okay? So when you don't have any horizontal or vertical movement, then your asymptotes are just the x and y axis. Okay? Y is the vertical, x is the horizontal. Let's see. So we've just got y equals 8 over x. So let's just pick a bunch of points and graph them and see what happens. Okay, there's no magic to this. It's just plugging it into a t-chart, right? So we've got y equals 8 over x. And they've just randomly picked negative 16, negative 8. It looks like multiples of 8 and factors of 8 is what they picked. Okay, negative 16, negative 8, negative 4, negative 2, negative 1, negative 1/2, and then the positive of these, 1/2, 1, 2, 4, 8, and 16. So when I plug in a negative 16 for x, I'm going to get negative 1/2 right there. And when I plug in a negative 8, I'm going to get y equals 8 over negative 8, which is just negative 1. When I plug in a negative 4 here, I'm going to get negative 2. And when I plug in a negative 2, I'm going to get negative 4. And when I plug in a negative 1, I'm just going to get negative 8. Okay? And so on and so forth with the rest of these charts. So after you fill in your chart with all these points and get enough that you get a good idea when you're beginning of how to graph this. So when we plot these, negative 16, negative 1/2, let's see, each unit is 4 here. So negative 16 is going to be back here, and negative 1/2 is just barely down. So there's that one. Negative 8 and 1, negative 4 and negative 2, negative 2 and negative 4, negative 1, negative 8, and negative 1/2, and negative 16 barely across that axis. Now, that's enough to say, okay, this guy's going to look like this. Okay, so there's your third quadrant. Now let's look at our positive values, 1/2 and 16, and when you plot all these points and you connect it with the smooth curve, you're going to get this. right? Now, remember, this goes on to infinity, and no matter what, it's never going to touch these axes. That's why they're asymptotes, okay? So the domain is all real numbers except for 0 in the range, right? And let's see, there's no x and y intercepts because it never crosses the axes, either axes, x or y, okay? Any questions about this? Okay, look at number 1 on your assignment. Your homework is to work everything through number 12, okay? So right now, let's just work on number 1 together. All right, so it says, we're going to do exactly what we just did. Graph the function, identify the x and y intercepts, and the asymptotes of the graph. Also state the domain and range. So you don't have to state the domain and range, okay? We know the asymptotes, right? Because right now there's no h or key value, so our asymptotes remain the x-axis and the y-axis, okay? So let's look at graphing this. You've got y equals -2 over x. I'm trying to figure out what I've drawn on this. So if you've got trying to clean this up a little. Right, so you've got y equals -2 over x right here. So now just pick some values. I randomly picked 1, 2, -1, and -2. So when you plug these in, -2 over 1 is just -2. And let's plot those points, 1 and -2. So down here. And next value, 2. When you input a 2, you're going to get -2 over 2, which is just -1. So now plot those. 2 and -1 is right there. Now that's enough right now for me just to take a quick guess and state, okay, that's where this guy's at. Now let's do the negative values. -1, well, -2 over -1 is a +2. So we're going to plug in -1 and 2, this point. And now -2 over -2 is just a +1. So now plot that, -2, +1. Now I can pretty much state, okay, that's in this quadrant at those points. All right, so there's my graph. Okay. It never crosses either axes, so they are vertical and horizontal asymptotes, and there's no x or y intercept. The domain and range are both all real numbers except for 0. Okay? Any questions on that? So at home tonight, over the weekend, you'll work 2 and 3, and let's move on to the next problem set. Now, I've made a little chart here. Each part of a graph of a reciprocal function is a branch, so we call these branches. The branches of the parent function, y equals 1 over x, are in quadrants 1 and 3. So I've got them marked with this stripy thing right here. Okay? There's your parents in quadrants 1 and 3. Stretches and compressions of your parent function will also remain in the same quadrant. So as you stretch or compress, it's not going to flip it over the axis. The only thing that's going to flip it into another quadrant is that negative sign on the A. So when you apply a stretch or compression, it's going to remain in this quadrant. Okay. So the reflection of these parent functions are in 2 and 4, the smiley face reflections. There's your reflections. That's when you have a negative A value. Okay. It gives you the smiley face ones. Okay. So parents are in 1 and 3. and the reflection is in 2 and 4. What it states is it's reflecting it over the x-axis. Okay. All right. Any questions? Let's look at problem 2. Identifying reciprocal function transformations. For each given value of a, how do the graphs of y equals 1 over x and y equals a over x compare? Well, we know the y equals 1 over x. That's that parent function in the first and third quadrant. They go through, they meet at 1, 1 and -1, -1, and they get really close to the axis at 4s and -4s. So let's graph that first. So that's the one in black, the middle one here. Let me see if I can highlight it in yellow. Okay. So there's 1, 1, -1, -1, and at about 4, it's super, super close. So now let's just fill that in. Okay, there's my parent function in black. So that's the y equals 1 over x. Now, they want to know, how does y equals a over x compare for a equals 6? So it's going to be y equals 6 over x. That's a 6 over x. So what you can do is plot out a t-chart and find what it looks like. I'm having trouble grabbing it. There we go. So you would plug in a t-chart for x and y for y equals 6 over x, and you would find that it gives you these values. And it's going to look something like this. It's going to go through these points and like that. So if a is equal to 6, is that a stretch or a compression? A stretch. And think about, on this black line right here, if I was to grab each end of that and stretch it, let's play like that's just a metal measuring tape that we've just sunk down into this quadrant. And if we pull on each end and try to straighten it up, what's it going to do? It's going to get wider, wider, and higher, higher. So that's what a stretch looks like for both quadrants. Everybody good with that? Now, let's do the same thing. Oh, before I move on, so we would say that y equals x 6 over x is a stretch of the parent function y equals 1 over x by a factor of 6. Okay, so it's higher up in the first and third, higher up in the first quadrant and lower in the third quadrant. Okay, that's what a stretch does. Now let's look at what happens when our a value is a compression or a shrink between 0 and 1. We've got 0.25. So again, the parent function isn't the one in black, the middle one here. Now, when you shrink it and you plug in some values in x and y and you calculate it and graph it, it gives you this one in blue. And again, think of the measuring tape and pressing the ends together and trying to compress it. It would allow that to go deeper into the pocket of those quadrants. Do you see that? That's what a compression does. So you would say, well, this y equal 0.25 over x is a compression by a factor of a quarter, or 0.25. And it pushes it deeper into the pockets, closer to that origin, okay, of the first and third quadrants. Any questions? Okay, and then here's a -6. And we can put these in a graphing calculator, which we'll do it pretty soon here. But again, you can use the same skills, but you know that this is just 6 over x and flipped over, right? But you know that the parent function is this 1 over x. There's that one. Now how does that compare to y equals negative 6 over x? Well, it would be the first one, or 6, but reflected over the x-axis. Okay, so you would just take those points and flip them down and up. So this is what they look like. So it is a stretch of 6 reflected over the x-axis. Okay? And if you forget all the rules in a test, just remember, you can always plot an XY chart. They're easy calculations. Just graph it. Pick four or 5 points and just graph them. Okay? Now problems 4, 5, and 6 go with this. Let's look at problem 4 together. Well, there we go. Problem 4 says graph the equation y equals 1 over x using and y equals a over x using the given value of a. Then identify the effect of a on the graph. So we know right away we're going to have 1, 1. So we've got 1, 2, 3, 4, 1, 2, 3, 4. All right, so we know the parent function is going to be at 1, 1, negative 1, 1, and by 4 it's going to be really, really close to the graph, the axis, excuse me. Oops, wrong one. So this one's going to be here. So here's my parent function, and negative 4. Okay, so that's crudely drawn in there. So there's my parent function. Now let's do a equal negative 3. So now we're going to have my a is negative 3. So I'm going to have negative 3 over x. So what we can do is just do a t-chart. Actually, let me do this. Okay. So if I have y equal negative 3 over x. So if I have x equal to negative 3, I'm going to have y a positive 1. If I have a negative 1 for x, I'm going to have a positive 3. And if I do a positive 1, and realize I can't use a 0 for x because it gives me an undefined number, right? So that's why we never touch the x-axis, or the y-axis, excuse me. So if we have 1, we've got a negative 3, and if I have a 3, I'm going to have a negative 1. So there's some points that will help me quickly graph this. So let me choose a different color. So negative 3 and positive 1 is there. Negative 1 and 3 is up here. So that sort of shows me it's going to be like that. And then over here, 1 and negative 3 down here, and 3 and negative 1 there. So it's going to do this and this. Whoops. So not that. It never crosses the axis. So what it is the a value of negative 3 reflects it across the x-axis and stretches it by a factor of 3. And that's what you would state. Okay? So, and a lot of times it's good just to mark this one's y equals 1 over x, and this one's y equal negative 3 over x. It's good to mark those in there. Okay? So you'll work 5 and 6 just like that. Any questions so far? Okay, just a couple of minutes, so I'm going to move on pretty quickly here. So now we've got we've learned what the a value does, the stretch and the compression. We've learned what the negative sign does, and flips it over the x-axis and the second and fourth quadrants. So now we're going to learn about the h and k value. Right? So our big formula here is right here. Y equals A over x minus h plus k. And x cannot equal h because that would make that denominator 0. So our A value is the shrink or the stretch, h is the horizontal movement, and k is the vertical movement. Okay? So that's our big formula. Now, let's look at how we're going to use it. And you know the parent function of this is going to be y equals 1 over x. Don't ever lose sight of that. Okay. So I copied this over here. So when you graph a translated reciprocal function, the good first step is just to draw your asymptotes. Okay? Now, here's a little trick I didn't point out. Let me back up. When you have an h and a k value, those become your new asymptotes. So when you translate, now your horizontal h and your vertical is k. So your vertical asymptote becomes x equal h. That becomes your vertical, x equal h. And your horizontal is your y equals k. Okay, so let's look. So draw your asymptotes. Oh, what is the graph of y equals 1 over x plus 1 minus 2? So we know we've got the parent function, y equals 1 over x, and then we've just got a horizontal of 1 and a vertical of negative 2. So really, it's that parent function translated to the left 1, so my h is equal to negative 1 because it was a plus 1, x minus negative 1, and my k value is negative 2. So these become my new asymptotes. So let's plot these. My h becomes my new vertical, and my k, the negative 2, becomes my new horizontal asymptote. Okay, so now if this is it, then we know we can just apply that parent function. So if we had the parent function, we said these are all by 2. Okay, so it'd be 1, 1, negative 1, 1, and by 4 it's really close. Here and here. So now you're just going to take each one of those points and scoot it over to the left 1 and down 2. And when you do, you'll get your new graphs, okay, in the blue. Okay, and again, you could just say, okay, it's going to go up 1 over 1, there's 1, down 1, left 1 and down 1. And then let's go by 2 units, it's really close, by 2 units, 2, 4, it's really, really close. You could do it that way too, just knowing it's a parent function, okay? Now, you will work problems 7, 8, and 9 like that. And then when you look at the next problem set, they're going to give you a graph and ask you to write the equation. So let's look at this. It says the graph, let's just look at your problem. Write an equation for the translation of y equals 3 over x that has the given asymptotes. So this goes with 10, 11, 12, and I'm looking at. So they give you x equals 0 and y equal 2, right? So we know that x is going to be my horizontal. So they give you, let's see, y equals 3 over x here. Let me get a new page. Okay, so if they tell you that your x is 0, so it's going to be x minus 0 plus k, which my y is equal to 2, so there's my k. So there's that x, and there's that y, the h and the k. All right, and now just clean it up. Y equals 3 over x plus 2, and that's all you're doing for those, okay? So plug them in so that x is your h and the y is your k, what they give you there. So those are really like 30-second problems. All right, and do these over the weekend, and that's everything. And I know that was hurried, but on Monday you've got Khan Academy, and then Tuesday we're going to do a big activity where you're going to get some clear paper and some markers, and you're going to do translations and move your clear paper around, have your graph on it, and translate it around. And then we will end up the session with you creating some of your own. After playing and learning more about the translations, you'll create some of your own problems. Okay? Any questions? All right. And then Wednesday we'll move on to 8-3. All right. Thank you. That concludes today's lesson.